Hello everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm your host for today's session. In these webinars, we try to bring a variety of topics that pertain to power system analysis and electrical safety. Claudio Mardegan with EngePower is our guest speaker in the past and is an EasyPower friend of long standing. Let me just say a few words about the material. First, this session will be longer than our typical webinar. It will run 90 minutes. We will provide an attendance certificate for everyone that attends today. It's an advanced level discussion of real-world systems. And something you won't often see is Claudio makes a connection between the system analysis and the information taking during a data log run on that system. We've pre-recorded his presentation to allow him to answer questions real time. He's agreed to join us today from Brazil, so please feel free to use the question box in the control of the webinar control box. And if we can't get to your question today, we will answer it via email. So again, thank you for attending today. And give me just a second and we'll start the presentation.
Hello, everyone. My name is Claudio Mardegan. Thank you for attending this webinar. You are very welcome today. This webinar is going to be divided in two parts because of the amount of information to be shared. This is my bio. The webinar agenda will be divided in 4 chapters. The first two, the first part, and the other 2 for the second part. Chapter 1, we are going to talk about the link between symmetrical components and harmonics and its importance for protection and filter grounding. The second chapter, we are going to talk about ground fault protection. Chapter 3, a better understanding on generator decrement curve. And chapter 4, overcurrent coordination. Chapter 1, here is the summary of the topics we are going to talk to. Basics on symmetrical components, the harmonics phase sequence, negative sequence effects on motors, harmonic effects, overheating machines, understanding the 5th, 7th, 11th, 13, etc. filter neutral grounding. Most of you have already studied symmetrical components. This tool is a math tool. In other words, when we apply it, we change to the math world. After performing the calculation, we must go back to the real world. As much time we use the symmetrical components, we will start associating physical effects to the mathematics entities. And these entities start having life in real world. Our main goal here is not just providing equations, but calculations, but also link both worlds. In early 1920s, field professionals detect that in non-symmetrical and unbalanced systems, when they measure the current in these circuits, the measured values did not match with the calculated values. That's when the need to create this tool came up to calculate the current correctly. The equations present on this slide means that the summation of the symmetrical components currents of each phase is obtained by adding the zero sequence current of phase A, the positive sequence of phase A, and the negative sequence of phase A. So for each phase, always will be the summation of the symmetrical components. And so you are able to, this equation is when you come back to the real world. But our friend Fortescue, that invented this tool, he provided us a very important addition, that is the phase sequence. He called positive sequence component. Is composed by 3 phasors of equal magnitudes with an angular phase shift of 120 degrees between them. So, symmetrical balanced system means same magnitude in all phases and same phase shift angle between phases for voltage and current. Thus, the phasor are represented just as shown in the slide. He had also the concept of phase sequence. He also adopted a direction of rotation as conventional, the counterclockwise. The meaning of that is if an observer is placed in the position indicated in the figure, you see the phasors rotating in a phase sequence ABC. So our observer sees the phasors rotating and passing A, B, and C phasors in this sequence. This is the positive sequence component. He also creates the negative sequence components. For a negative sequence component, the principle is the same. The main difference is that Fortescue reversed 2 phases, B and C. All we know that for motors, if we reverse 2 phases, the motor will change the rotation direction. So the observer will see the phasors rotating at the phase sequence ACB. So now, when the vectors start rotating, the phase sequence that the observer will see is ACB. Okay, the meaning of that is that for negative sequence components, the true rotating direction will be clockwise, because conventionally is counterclockwise. But since he reversed the 2 phases, the true rotation direction will be clockwise. After this explanation, it's easy to understand that positive sequence current generate accelerating torques in a motor, whereas negative sequence currents generate restraining torques. When this happens, it's just like increase the load in the motor, which means increasing the current. Increasing the current, the motor will overheat. Thus, the negative sequence function protection is, in the first instance, thermal protection for stator windings of rotating machines. Negative sequence protection can also be applied for other purposes. Zero sequence component. Zero sequence components are formed by three equal magnitude phasors with the same phase shift angle. In other words, the phasors are in phase. The observer will see them just like one, just like would be one. So the phasors will be in phase, the same phase shift angle, and also rotates counterclockwise. Understand what Fortescue wants to show us. This slide was created with the aim of showing what the Fortescue tool provides. From the symmetrical components, we are going to perform the phasor summation to reach a phase magnitude. To get the phase A resultant, we have to sum the positive sequence current for phase A, negative sequence for phase A, and zero sequence for phase A. So, vectorial sum, we start with the first phasor, and we put the second phasor, the beginning of the second phasor, at the end of the first one. So this is the position of the second vector. The third vector uses the same philosophy, the beginning at the end of the last one. So the resultant for phase A, we will start from the beginning of the first phasor to the end of the last one. This is the resultant for phase A. We can do the same for phase B, placing the positive sequence phasor for phase B, negative sequence for phase B, and zero sequence for phase B. The resultant will be the one showed here. Doing the same for phase C, we take the phase C phasor of zeros, positive sequence, negative sequence phasor for phase C, and zero sequence phase C. The resultant for phase C is this one. So this is the resultant phasor for phase C. If we put all the three resultants phasors in the same origin, we are going to have this. As we can see here, we don't have a balanced system. Why not? Because the phasors don't have the same magnitude, neither the same phase shift angle. Concluding that what Fortescue did for us is taking this system that is completely unbalanced and transform it in 3 balanced systems. Why Fortescue did this? For a special reason. The application of phasor theory is only applied if the currents are sinusoidal. Okay, that's why shall be done this way. If you don't do this, what you measure in field will not match with the calculated values. Okay? Good. Another important thing is that harmonics has also phase sequencing. The characteristic harmonics are generated by this equation here. NP plus or minus 1, on where H is the harmonic order generated, N is an integer number, P is the number of pulses of a converter. So the most common converter, we have 6 pulses. For N equals to 1, we have 6 minus 1, the 5th order harmonic. 6 plus 1, the 7th order harmonics. So we have this characteristics harmonics, the 5th and the 7th. For N equals 2, the process is the same. We are going to have 11th and the 13th order. Harmonics that are multiple of 3 are 0 sequence harmonics. So this pattern here doesn't change. Harmonic of order 1 is the fundamental frequency, 6 Hertz or 50 Hertz, depending on the country. But this is the fundamental, is positive sequencing. The second order is negative sequencing. This third order is 0 sequencing. And this pattern also repeats. Okay? That's a very important thing. And as you can see here, that's very, very important. I am trying to emphasize because it's the most common and one of the most, one of the highest magnitude harmonic is the 5th order. So it's negative sequence here, okay? But another way of reach the harmonic order is providing, just like showed here. For a balanced system, at the fundamental frequency, the current will be Imax sine of omega t For phase B, the same with phase shift angle of minus 120, and for phase C, plus 120. For second order harmonic, we have to multiply the arguments here by 2. That means second order harmonic is 2 times faster than the fundamental. If we multiply the arguments by 2 here, we are going to have these equations here. The first one, the phase shift angle is 0 because here is 0. When we multiply here by 2, what we have? Minus 240. That is the same plus 120. If we multiply this equation, this argument here, by 2, we have 240 positive. That is the same as minus 120. If we take a look here, we see that the position of phasor B relatively to this phasor C, they reversed the position. This means that second order harmonic is a negative sequence harmonic. So, proving that this pattern here is correct. Okay, if we do this for the third order and multiply by 3, we are going to see that the 3 phasors will be in phase. When a third order harmonics reaches the neutral point of a transformer, a generator, the currents, the summation will not be 0, but they will be at themselves. Okay? The fourth order, we multiply by 4. So the position of the vector are the same as positive sequence. So is a positive sequence harmonics. For the fifth order, we see here that the vectors change the phase shift angle between phase B and C. And this means that is a negative sequence harmonic order. The sixth harmonic is 0 sequence harmonics. Okay? So we could demonstrate for other orders, but the process is the same. Harmonic effects over rotating machines are listed on the slide. Overheating, vibration, noise, torque changes, increasing iron losses, increasing joules losses, reduction of machine life expectation, efficiency reduction. What happens is that positive sequence rotates counterclockwise, and the fifth order is clockwise and running on a higher speed, 5 times higher. Okay. What are the sequences generated by that equation we showed to you for the characteristic harmonics? We saw that there are some positive sequences, harmonic orders, some negative sequence harmonic orders, and 0-6 harmonic order. Okay? So, the positive sequence harmonic orders, the summation of the three currents or the three voltages always will be equals to 0, the summation, because they have the same magnitude and they are 120 degrees offset of each other. So the summation is 0. So for positive sequence filters, the neutral grounding of the filters are not required, because always the summation will be 0 at the neutral point. The same thing happens for the negative sequence currents. The summation of the three currents will be 0 at the neutral point. So filter neutral point is not grounded. But for zero sequence harmonics, the summation of the three phases is not 0. So the filter neutral point shall be grounded. Okay? Good. About negative sequence, there's something very important to note that I didn't tell you, but for negative sequence, just like fifth order harmonic, we told that there is a restraining torque that provides more current to the motor, overheating the motor. That's the reason that negative sequence currents and negative sequence protection at first instance is stator thermal winding protection, because we overheat. And we see by the digital fault recorders that many motors burn because of harmonics. And the most dangerous for overheatings are the negative sequence harmonics, the 5th, 11th, that they have magnitudes that are more relevant. Okay? Now we are going to start chapter 2. Ground fault protection. We are going to talk about the full equation to calculate the single line to ground short circuit currents, charging currents, the effect of charging currents on overcurrent protection, and special real-world case using zig-zag transformer for cellulose and paper mill plants. This is a very interesting experience I had here in Brazil. The biggest plant here in Brazil, we provide most power system analysis studies for them, and we have a very nice expertise on that. So a very important thing to say here is that most commercial software, they don't calculate the charging current. And this charging current interferes on the ground protection significantly. So that's why we decide to show you here. Okay, so in this chapter, we are going to discuss some important topics related to single line to ground current, including complete fault current equation. This complete fault current equation, you take into account also the fault impedance and arc resistance. That's what we intend to show you. Bolted single line to ground fault. This slide, we intend to show you the demonstration of the equation for the single line to ground bolted fault. Okay, so in a bolted line to ground short circuit, one phase goes to ground and the other two phases remain healthy. For the deduction of the bolted single line to ground short circuit current, the theory of symmetrical components is used. This means that we have to go to the math world. This type of fault is characterized by, normally, by the insulation failure between one phase and ground. To demonstrate this, we have to place here the boundary conditions. For a single line to ground fault, the voltage at the phase A, that is the faulty phase, goes to zero potential. And since the short circuit currents normally are very high or are greater than the full load amps of the other phases, most of the literatures assume that IB equals IC equals 0 for phase B and C. So now we have to go to the math world. To go to the math world, all we know that the zero sequence current is given by this equation, the positive sequence, this equation, and negative sequence, this equation. Take into account the boundary conditions. IB equals IC equals 0. We replace these values here in this equation. So we are going to have IA0. And the result is that is 1/3 of IA. Doing the same for the positive sequence, IA1 equals to 1/3 of IA. And doing the same for the negative sequence, we reach the same result, 1/3 of IA. In other words, these three circuits have the same current, meaning they are series connected. So it's what this figure is showing right now. Now we have a simple circuit with one loop and one source. The current can be calculated by the voltage source divided by the summation of zero sequence impedance, positive sequence impedance, negative sequence impedance, plus 3ZG. ZG is the grounding of our sources. Transformer, electrically speaking, is the neutral secondary side of transformer, is the voltage source for the electric circuit from that level of voltage. The same for the generator. So ZG is the impedance connected between the neutral and the ground. Okay. IA 0, I am in the math world. I have to come back to the real world. I have to reach or to get the IA value. Looking at this first equation here, IA is 3 times IA0. So to reach the final single line to ground short circuit is just to multiply IA0 by 3. And the final result is this one. For phase B and C, the currents by the boundary conditions are 0. And this type of short circuit is an unbalanced short circuit because for phase B and C, the current is 0. Okay? The single line to ground bolted fault, the equation is this one. Including the fault impedance, remember that the fault impedance is connected between the phase and ground, differently of ZG that's connected between the neutral and ground. But we have zero sequence impedance fault, positive sequence and negative sequence fault. So normally they are the same 3 times this value. Is different from this 3 times because here is from neutral to ground. Here is between phase and ground. And for arc impedance, but arc normally has a resistive behavior, so is 3 times the resistance of the arc. Okay, this is the full equation. Okay, before I going ahead, we have to provide some definitions. And in case of medium voltage insulated cables, let me see. Before saying that, let's give the definition of capacitance. 2 conductors separated by a dielectric material form a capacitance. So when you see an overhead transmission line, you have the conductor, that is, you have the cable of the line, that's a conductor. You have the insulation, is the air. You have the ground, that's also a conductor. So you have a big capacitance, a distributed capacitance in the line. Okay, when you have medium voltage cable, you have the same. You have the conductor, you have the insulation, you have the shield. For low voltage, you have the conductor, you have insulation, you have the infrastructure. For electrical machines, you have the wire of the winding, the insulation, and you have the starter of the machine. So all electrical equipment born with a capacitance. You cannot see it, it's not a capacitor. Capacitor is an equipment, but trap capacitance is something that really exists and born naturally, if you want, or not born with the equipment. In English, normally it is known as trap capacitance. That means that is an intrinsic capacitance, because born with it. So when you energize this equipment, this charging capacitance, they charge themselves, and a current starts flowing on that. This current that flows in this capacitance, this current is known as charging currents. Okay? Good. The ideal modeling of an insulation is a resistance in parallel with the capacitance. In the previous slide, we showed you that all equipment born with this capacitance. So this really exists. But when you are measuring with a megometer, you don't measure the capacitance because the source of the megometer is a DC source. So what you are measuring is the DC resistance of the insulation. So that's why the ideal modeling of an insulation is a capacitance in parallel with the resistance. How to calculate the charging current? Normally is the line to ground voltage divided by the X0, that is the charging reactance, is a capacitive reactance. And that equals 1 divided by omega C0. If you, we are going to show that when a fault happens in an unground or resistor grounded system, appears a current equals to 3 IC0. And this 3 IC0 is calculated multiplying this equation by 3. This is done here. Okay? We are going to show you why is 3 IC0. So, charging current calculations in HRG systems, high resistance ground systems. Huh? If phase A goes to ground, this current here is the total ground fault current. Part of this current returned by the resistor, part of the current returned by the capacitance. But the phase at the phase A capacitance doesn't flow current here because this side of this capacitance is ground. And when single line to ground fault happens here, we are shorting this capacitance here. So, but when this goes to ground, these other two phases will raise off square root of 3. And when we add these two vectorally, these two currents, we are going to have the 3 IC0. Charging current. In an ungrounded system, for instance, or HRG systems, these currents are very low. For low volt systems, normally IC0 is about 1 amp. But for medium voltage systems nowadays, these currents can be very, very high. But let's see what happens here. I put this phasor with a phase shift angle minus 90 degrees. So here is plus 30 degrees, and this one is 150 degrees. That is the same minus 220 degrees. For the definition of IC0 current equals the line to ground voltage divided by minus JX0. Minus J is the same of minus 90 degrees. That when goes to the numerator, minus 90 degrees changes to plus 90 degrees. Plus minus 90 degrees, the charging current for phase A is at a phase shift angle of 0 degrees. So it's 90 degrees leading the voltage. Why is 90 degrees? Because of the minus J is leading, okay? For phase B is the same. If we divide by minus JX0, minus 90 degrees goes to the numerator with plus 90 degrees. We are going to have this phase angle here. So it's also 90 degrees leading. For phase C, 30 degrees plus 9 degrees, 120. So before a ground fault happens in HRG systems, these currents are balanced. And so they have the same magnitude and the same phase shift angle. And the three currents summation equals to 0. Okay? What we can see here, there is something very, very important happening here. Okay? The understanding of this is extremely important. We discussed this almost 1 year, and we were writing the chapter 1 of 3003 series, and we didn't reach in a consensus, so we didn't put this on the book, but I'm going to show you the correct and correct directions of these vectorial summations, okay? So, what we can see here, before a fault, we had VA here. When this phase goes to ground, this arrow here goes to the 0 potential. But since you are ungrounded or high resistance ground, the neutral will offset relatively to the ground. So the potential now, the ground potential is 0, but the neutral is greater than 0. So this phasor between the neutral and ground right now is 108 degrees from VA. And the summation of these two voltages will give us the new voltage for this unfault phase here. So the voltage relatively to the ground is no longer VC, but V prime C. And this angle is 60 degrees, just like shown here. Here is the line to ground voltage with 90 degrees, with this one with 30 degrees. So what we reach, the magnitude raises to a new value given by the square root of 3 single line to ground voltage. And this angle is 60 degrees. For phase C is the same. We have to sum this vector here with this one in order you reach this. And the summation gives us this result. Also, the magnitude raises of the square root of 3, but this new angle will be 6 more 6 degrees. That is 120 degrees. The new voltage relatively to the ground will be no longer VB, but V prime B. The neutral ground volt is minus VAN, which is equal to VA0 equals 1/3 of the single line to ground times square root of 3 times square root of 3. Here you're going to have 3 that cut with the 1/3 here. So we have line to ground voltage with 90 degrees. VNG, so is at this position here. So VA0 is 1/3 of VA plus VB plus VC, replacing their values here. We see that VA0 is the same value of VNG. Okay? Charge current calculations in HRG systems. Now, after a ground fault, what the current in the resistor will be VNG divided by R. VNG is minus VAN divided by R. So the final magnitude of IR is this value. And you see that IR in phase with the voltage that promotes the voltage of neutral voltage offset. That is very important. Total charging current during the fault will be IC0, single line to ground fault, divided by minus X0, JX0. minus J is the same as minus 90 degrees. That goes to the numerator, changing the sign. And here, but since the voltage is 0, this current is 0. For phase B, we are going to have VB times the square root of 3 with a phase shift angle of 120, divided by minus JX0. Minus J goes to the numerator as 90 degrees, and we are going to have IC0 magnitude times the square root of 3 with a phase shift angle of 220, 210. So, the charging current for phase C in the fault condition will be VC times square root of 3 with a phase shift angle of plus 60 degrees, resulting in a current of IC0 times square root of 3 is a phase shift angle of 150. So one IC0B is here, 210 degrees, and IC0C is here. The vectorial summation of these two currents will give us 3 IC0. So the 3 IC0 appears because of the voltage at the unfault phases will raise of square root of 3, and due to the vectorial sum of the currents will lead to the 3 IC0. Okay, good. A few years after the discussion we had about the direction of the currents, an event happened in a paper and pulp mill plant here in Brazil in 2015. Is in the 34.5 kV level. And we had the digital fault recorder, and we analyzed this event for the customer. So this is the online diagram for this event. This plant is a huge plant, but here we put just what is interesting for us. Okay, so the utility supply through this transformer here. We have also 2 turbo generators, 13.8, and the step-up transformer to 34.5 kV. Connecting these 2 switch gears, we have a current limiting protector here. Is a IS limiter from ABB. Okay, so the expected ground fault current magnitude should be 400 plus 150 plus 150. So the total ground fault at this voltage level, the maximum ground fault, this voltage level, the expected one is 700 amps. Okay? Good. One day, this IED tripped, indicating ground fault. Ground fault. So I tripped this breaker here and opened the circuit. Everyone thought that it was a ground fault on this circuit. But this is the digital fault recorder that we use in a training we have here to analyze digital fault recorder. So I positioned the cursor before the fault. So the voltages, the first 4 lines are the phase A, B, C, and 0 sequence current. And the other 4 lines are for the voltage, VA, VB, and VC, and 0 sequence voltage. Since the cursor is before the fault, the voltages are the single line to ground voltage. Okay, the current is 0 sequence current, is near 0. And also the 0 sequence voltage is very, very low. Okay? But positioning the cursor here, what we see in this figure, we can see that the phase that went to ground is phase C. And the voltage raised on the other 2 phases. And this means that it's a ground fault because the system is low resistance grounded. Okay? But what I can show you here with the cursor at this position, we see that the ground fault is 14 amps, 14.5 amps. The expected value was 700 amps, 700 amps. So, too much higher than the expected value. Taking a look more close to the vectorial diagram, what we see here, channel 8 1, 2, 3, 4, 5, 6, 7, 8 is the 0 sequence voltage, is at almost 90 degrees, as we showed in the vectorial diagrams we showed you before in previous slides. And here, channel 4 is the 0 sequence that's almost 90 degrees, leading the voltage, and the phase shift angle almost 108, just like we showed. The unfaulted phase 60 degrees here and 110 degrees here, just like we showed. So, the vectorial diagram we provide to you, it really reflects the correct directions of the currents. Okay? So, this is very, very important. So, another interesting thing to show you, these slides I prepared to you based on my guru, Dunk Jacobs. Dunk Jacobs wrote a book, Industrial Ground Design Handbook. And as can be seen, the capacitance between the phases do not affect single line to ground faults. We showed that we have these capacitance that born with equipment that are the trap capacitance. And also between the phases, we have capacitance. But these capacitance don't affect single line to ground faults, neither over voltage, line to ground over voltage. And so the first approximation circuit could be written just like this one. Applying Thevenin theory seen by phase A, we have to short it voltage in order to get the equivalent impedance. So if we do this, X0 is much higher than this impedance here. So we can bring it to the neutral. This one, the same. This one, the same. So this circuit here, this three-phase circuit here, can be written as a single phase, just like this one on the left here. And this circuit is very, very, very important because this figure can show you when X0 is important or not, when X0 takes effect or not. So if we have here a solidly ground system, ZG will be shortened, and also X0 is shortened. So for solid ground systems, X0 is not relevant, right? But for ungrounded system, ZG practically equals to infinite. So X0 is relevant. And for resistance ground systems, we have this. And showing this and looking at this, when R is very high, most of the current will flow by the capacitance. So the equivalent current will be capacitive. When the current flowing is capacity to the ground, means that the system, you think you are resistance grounded by the behavior of the systems. The system will behave as a non-grounded system. And you may have transient over voltage, ferroresonance, and etc. So when the resistance value is lower than X0 over 3, is lower than, most of the current will flow through the resistance. So you have resistive current, equivalent resistive current for the system. So the system is considered grounded. The linear between ground or unground is given by this equation. Okay? Here is a resistive current. System is considered grounded. Here is a capacitive current. Systems ungrounded. Okay, good. System with long cable run. This example here is in a paper I wrote for IEEE, but I put it here in order to show you the cable length can interfere on the grounding coordination. Okay, so this is a summary. This is a transformer that is a low resistance ground. Here we have instantaneous ground fault protection set to 15 amps. A ground fault happened here. This first one, relay tripped, but this one tripped too. Why? Let's see. This cable is 600 MCM, 5 kilometers. The capacitive impedance given in the manufacturer's cable parameters, 4,530. Okay, how we calculated the XC? Since here is times kilometer, we have to divide by the kilometer. Why this cable run is so long? Huh? Because here is a effluent treatment plant that normally is distant from the switch gear. So you have 906 ohms. The IC0 current will be the single line to ground voltage, that is the line-to-line voltage divided by square root of 3, divided by 905 ohms, 906 ohms, and given us 8.8 amps. 3IC0 will be 26.4. What this means? The setting of this relay is 15. Since this current, charging current, reached 26, contributing to the fault current in this direction here, tripped this circuit too. Okay? But this is a misoperation. It should not trip. So there's a way to warn you if the cable lane is relevant or not. I demonstrate it in a paper I wrote. The equation is this one here, XC of the cable parameters data times primary amps setting of the relay, divided by square root of 3 and line-to-line voltage. For our example here, if we put these values here, 15 amps, right? The critical length over 2.8 kilometers, we can trip wrongly our relays. So this is a warning for us. When this happens, what can we do? two solutions come up. Normally, the first one is to provide a delay for these circuits with long distance. But we increase the delay and the total clearing time. The other solution is to provide, to use directional elements, looking to the load, not to the source. So that's what we can do. Okay. This example here is that one I told you that happened in a paper and pulp mill plant. And it's interesting to see what happened here. The manufacturers provide us the cable electrical parameters, and the values used here are highlighted in this red box here. Okay. This switchgear here, we see we have 17 outgoing feeders and very long cable runs with many conductors per phase. This is a huge plant in Brazil. Okay. How we calculate the charge current in a system like this? What we do, we can put all the circuits in a spreadsheet. The number of conductors per phase, the cross-section, the cable length, the electrical parameter given by the manufacturer. These two columns are calculated as shown here. XC will be this value divided by this and divided by the number of conductors per phase. So we are going to have this value here. And the charging capacitance will be 10 to the 6th power to have the results in microfarads, divided by XC times omega. So if we provide this calculation, we will match with the values we calculated here. Okay. Since this is a spreadsheet, you copy the formula for the other cells, and you have the summation of the charging capacitance for this level of voltage. Here we have the transformer capacitance and also the switchgear capacitance. These capacitance were calculated as shown here based on the IEEE literatures. Okay. So the cable capacitance, transformer capacitance, switchgear capacitance. As you can see, what is prevalent here is cable and line capacitance. With the total capacitance, I can calculate the capacitive reactance of the charging, and we have 386.89 ohms. IC0 will be line-to-line volt divided by square root of 3 divided by the XC. and we reach 51.5 amps. 3 IC0, 154.5 amps. Since our system is 100 amps grounding resistor, our customer thought he was low resistance ground, but in fact, the system behavior was just like an ungrounded system. And this was comproved by the digital fault recorders we had, and due to the events that happened, the main warning for us is that when you have a ground fault in a specific location and simultaneously you have other ground faults in other locations, this is a warning for us that our systems are not behaving as a grounded system. Okay? Good. So, for newer paper and pulp mill plants, most simple solution is to raise resistor amps. But sometimes doing just this is not enough. Okay? The design protection engineer have to find solution considering other issues. Other issues normally not known. I try to point out these details for you. The parameters to take into account are size of the resistor, short time amps, rated continuous current of the resistor, system charging current, number of sources in operation, diversity of operation, because you have turbo generators, you have utility, and when you have to provide an overhaul for a generator, for instance, you are going to lose a generation and a grounding, so you are losing a resistive current. So the capacitive current can become prevalent. So that's what you have to take in consideration. Cable shields, protection total clearing time, need of a zig-zag ground yaw transformer installation. That's what we provide. So some required parameters are written here. Resistor short time current, sum of resistor short time current for all sources, nominal continuous Dutch current of the resistor. This is something that most of the guys never thought about, because what you have in the nameplate of the resistor is the short time current. How much current the resistor is able to carry continuously? That's the questions. You have to buy the resistor with this continuous capacity, because when you provide a setting, a ground fault setting for a relay up to this value, if this current flows in the resistor, you are going to burn the resistor if the resistor was not designed to withstand this. Cable shield damage curve. Shield was not designed for short circuit flow. The main goal of the shield is to provide a radial and equal distribution of the electric fields inside the cable. The magnitude of total system charging current is 3IC0. So we have to calculate it. Earth fault clearing time, that is the protection time plus interruption time, diversity of operating conditions. You have different operation conditions. I have today some plants, they have 3 utility transformers and 4 400 MVA generators, for instance. So it's huge plants. Need of installation of a zig-zag transformer. Okay. Resistor short time current. The resistor short time current shall be chosen based on the 3IC0 current. As we showed before, the resistive current shall be greater than the 3IC0. Okay, this means that this angle showed here shall be lower than 45 degrees. Resistor continuous Dutch current. We have already talked about it. If you have a setting up to the current setting, the resistor shall be able to carry this current continuously. Otherwise, the resistor can be burned, can be damaged. Okay? If a resistor damaged, it burns and the resistor opens the circuit. And if the circuit is open, you become ungrounded and you have all the disadvantages you have for the ungrounded system. Shield damage curve is calculated by ICEA standard and IC. And this is the equation you have to calculate if the current, which is the current that this shield is able to carry, and the time the shield is able to withstand. Okay? System charging current can be calculated as we showed before, and the total fault clearing time can be set based on all of this we talked about. All these parameters we talk about have to be integrated in order you can provide a good design. So this is a small piece of the system we have. So here we have 2 utility transformers, 3 turbo generators. The charging current here, this is 3IC0 for this bus, 3IC0 for this bus, 3IC0 for this bus. What we provided here, in order we can have any operational condition, is provide a zig-zag auto transformer here, limiting the current just above the 3AC0. Doing this, we will not depend on the resistance of our sources. You see, that's the philosophy that was used here. Here is the short circuit current limiter, the clips. 3IC0 is this value. If we sum all the resistance, we have this value. So the total ground fault will be this value. The maximum clearing time for this system is with a conventional medium voltage cable cross-section. If you want to raise this time, you have to buy cables with cross-section greater than conventional cross-section. Okay, so this is what we have for you today. I hope this information can help you on your studies. In a month, we are going to have the second part, and we are going to talk about the generator decrement curve and coordination. We are going to talk about conventional coordination and also logical coordination. And I wait you there. If you have questions, please, you may ask me. Okay, thank you very much. Thank you for the opportunity, and have a great day.